Okay, we discussed graphs in general. From this point on, we are going to focus on trees. And trees are, in fact, special types of graphs. A tree is a connected, undirected graph with no simple circuits. Okay, so you cannot find a circuit in a tree. This means from one vertex to another, if there is a path, there is a unique path. So an undirected graph is a tree if and only if there is a unique simple path between any pair of vertices. So such a tree, for instance, when you look at it, from this vertex to this, the path is this. There is no alternative path because alternative path means if you have an alternative path, you have a cycle, and that's not allowed in a tree. Okay, so we have some terminology here. Of course, similar to subgraphs, we have subtrees. The definition is the same. You have a subset of vertices, subset of edges, and we have the concept of a root, as we have seen in graph traversal. It's the same concept. And we have, with respect to the root, we have leaves that are the vertices at the lowest level, if you will. And we have the concept of children and parents. So these two are children of this vertex, which we call the parent of these leaves. And this leaf is a child of this vertex, and this vertex is a child of the root. And these all vertices we call the descendants of the root. And the vertices, if you select this as the root, the vertices that are not leaves are called internal vertices, and they are shown in this picture. And also we have the concept of siblings, the vertices that are children of the same vertex. So this is the set of terminology we use when dealing with trees. And we also have the concept of m-ary trees. A rooted tree is an m-ary tree if every internal vertex has at most m children. So this is sometimes confused when you say, for instance, a binary tree. This means every internal vertex, meaning the ones except the leaves, has at most 2 children. So, for instance, this is a lot. Okay, so you just have one child here, and that is allowed. What is not allowed is more than 2. If you have more than 2, for instance, if you have 3 here, this is not a binary tree, but a ternary tree, a tree with 3 children at most for every vertex. So this at most is important. Do not forget this. It doesn't say, for instance, for a binary tree does not have to have 2 children at every internal vertex. Now, based on the definition of a tree, we have a number of results here, which I will not go into the details, but most of them can be proven using basic algebra or induction. So I'm just going to give them. A tree with n vertices has n-1 edges, and that's quite trivial because you start with, again, the basis case of a single vertex, which will have n-1 equals 0 edges. And you can apply induction on this by addition of new vertices, which will have to connect to one of the internal vertices or the leaves, and therefore it will produce just one additional edge. So you can use induction to prove this theorem. Another theorem is regarding m-ary trees, a full m-ary tree, and by full we mean, now as I said here, an m-ary tree does not have to have m children at every internal vertex, but at most. When we say a full m-ary tree, we mean that this tree has exactly m children at each internal vertex. Okay, full m-ary tree. A full m-ary tree with I internal vertices contains m times I plus 1 vertices. So you can actually prove this because each one will have m, and you can apply simple algebra to prove this, not that difficult. Another one, a full m-ary tree with this many vertices and internal vertices and leaves. So this theorem gives you the relationship between the number of internal vertices and leaves and total vertices. So I'm not going to go into details, and you can usually show that these are true by simple arithmetic. Now, these definitions are important. The level of a vertex is the length of the path from the vertex to the root. So for instance, if you have this vertex here, a path of 1 here, a path of 2 here, a path of 3 here, if this is the root, the level of this vertex is 3. The level of this one is 1, the level of this one is 1, the level of this is 2. The height of a rooted tree is the maximum of the levels of the leaves. You just look at the leaves, find the levels, and the maximum gives you the height of the rooted tree. Now, the selection of the root is significant here because in a tree, any vertex can be selected as the root, but when you change the root, the height of the tree might change. And balanced is an important concept. A rooted m-ary tree of height h is balanced if all leaves are at levels h or h minus 1. Okay, so you have, let's say, a binary tree. Okay, this is a binary tree where you have level 0 here, level 1 here, level 2 here, and level 3 with this leaf. So you have 1, 2, 3, 4 leaves in this tree, in this binary tree. And the level of these are 2. The level of this one is 3. Okay, which satisfies the definition. All leaves are at levels of h or h minus 1 because this is a tree with height 3. Okay, so this is a balanced tree. A balanced tree doesn't have to be full. You don't have to have every vertex here. For instance, this doesn't have to be like this, doesn't have to be full. But for instance, if you have another edge here, then this will have level 3, this will have level 4, this will have level 2, which will not satisfy the definition, so it will not be a balanced tree. Another theorem, again, you can prove by induction, is regarding the height of this balanced tree. There are at most m to the h leaves in an m-ary tree of height h. Well, this is not that difficult to prove because you will just consider the case where you have all vertices having children at the final level, and m to the h is going to be not that difficult to prove using induction. You will start with the basic step of a single vertex as the root, and that will refer to m to power 0, and then prove using induction.